Hey everyone, welcome back to physics. This will be lecture 6 of the course, and this will be the last lecture for this first big section, motion along a straight line. So we want to always end all of the big sections with a lecture devoted to just problems and examples. So lots of examples. It really can't be overstated. You really can't overstate the importance of examples and problems in physics. This is true of any mathematical discipline, but physics in particular, I feel that when you're working out lots of different problems and examples that are based in the real world, physics really starts to shine. It's really a lot of your comprehension comes from really studying different physical examples. So that we're going to be doing that at the end of all of the large sections in the course, and so this will be our first one. So let's go ahead and jump into it. We'll call this section 1.6, Problems and Examples, and specifically problems and examples from on the topic of motion along a straight line. So I've got a couple of examples. We'll start with an example that deals with up and down motion. Okay, and so the concept of free fall is going to be looked into. So up and down motion. Okay, and let me just kind of read the entire problem to you, then I'll write it down, and then we'll talk it through. So here's the problem. You throw a ball, you're positioned on the top of a building, at the edge of the top of a building. You throw a ball vertically upward from the roof of this tall building, and the ball leaves your hand with an upward speed of 15 meters per second, and then the ball is in free fall. Okay, so that's the physical scenario, and then we'll have a series of quantities that we want to calculate given this scenario. So you throw a ball vertically upward. From the roof of a tall building. From the roof of a tall building. Right, and I'm just going to say here, assume everything is idealized, right? What do I mean by that? Well, I just mean, the ball's going to go up and it's going to come down, and we're going to say that it doesn't land right on the building. And so technically I'm going to stand at the edge of the building, I'm going to throw it up right at the edge, and when it comes down, it's going to go right past the building. It's not going to hit it, right? So, and also, we're not going to worry about wind resistance, and we're not going to worry about side draft, wind coming at the ball from the side, throwing it off course. So we're just going to assume everything is idealized, right? So you're standing on top of a building, and you throw this ball vertically upward from the roof. The ball leaves your hand. It leaves your hand with an upward speed of 15 meters per second. And then once it leaves your hand, we say that the ball is in free fall, right? So the only force acting on the ball as soon as it leaves your hand is the force of gravity. Okay, so we've got 4 quantities that we want to calculate. Well, first let me draw a light little picture here. Right, so here you've got your building, okay, and you throw the ball. The ball is positioned at the top of the building, and you throw it upward at 15 meters per second. So we'll call this time 0, right, when the ball is in your hand on top of the building. And so its initial velocity also is given 15 meters per second, right? So it goes up at 15 meters per second. It's going to hit some kind of a peak, and then it's going to come back down. Okay, so that's the scenario. Pretty simple. You're standing at the edge of the building, you throw it up, it comes down. Okay, no other forces acting on it. So what are we interested in here? Well, we want to find first the position and velocity. So we're going to find a bunch of things here. So we want to find first the position and velocity of the ball 1 second and 4 seconds after leaving your hand. Okay, so that's part A. All right, then after that, part B, we want to find the velocity when the ball, so we want, here we're interested in the velocity. Find the velocity of the ball. Find the velocity of the ball when it is 5 meters above the building. Okay, so it's, 5 meters above the building, so maybe that's somewhere like right in there, something like that. How fast is it going in the upward direction once it's 5 meters off the top of the building? Okay, and then part C, we want to know the max height reached by the ball. The max height reached by the ball. Okay. Okay, and then finally part D, the acceleration of the ball when it's at its max height. What is the acceleration of the ball when it is at its max height? Okay, all right. So what I recommend as we're going through problems like this is, once the problem's been fully articulated as it has here, I recommend you pause the video and try to work it out yourself, right? I highly recommend doing that. If you, it's totally up to you, obviously, but if you simply watch me work out the problem, then you don't struggle with all the decision points that come up when you're facing a new type of physics problem. Right, so I highly recommend pausing the video now. Spending a problem like this probably takes 10 or 15 minutes. I highly recommend pausing the video now. Spend 10 or 15 minutes trying to figure it out, come up with some solutions, and then hit play and see if your solution agrees with mine. I highly recommend that. Okay, all right. So let's go ahead and take a look at the solution here. There's different ways to solve a problem like this, and we'll choose a way. Okay, so for part A, remember we're interested in the position and velocity of the ball at certain times. So there are two kinematics equations we could use, right? So we're on part A. So we can use, there's different ways to do this, but one way to do it would be to use this position formula, y equals, so final position, y final equals initial position plus initial velocity times t plus 1/2 acceleration times t squared. So this would be like a nice position function you could use. All right, and then for the velocity part of the problem, you could use this. Velocity final is equal to the initial velocity plus the acceleration times the time. Now, so these are two expressions you should probably use for this, right? These are the most straightforward way to tackle this. Now, what is the acceleration? In order for these to work, what do we have to know about acceleration? Constant. And since the ball is in free fall from the moment it leaves your hand, we have constant acceleration. So we have constant acceleration. What is that acceleration? We have constant acceleration of g equals 9.8 meters per second squared in the direction, in the downward direction. So we'll use negative 9.8 meters per second squared. All right, so important to come up with a coordinate system for problems like this kind of at the onset. This one is so simple that I don't emphasize it, but really you want to be thinking of the x-axis, and then the vertical is the y-axis, right? And so downward would be negative, upward, when the ball leaves your hand, it's traveling in the upward direction, so it has positive velocity, right? But throughout this whole scenario, the acceleration is downward, negative 9.8 meters per second squared. Okay, all right, so we have the constant acceleration, and we have two expressions that we can use to calculate these things. So let's go ahead and do so. So let's start by plugging in the known quantities. So position as a function of time is equal to y naught plus v naught t plus 1/2 g t squared, right? And so if I plug in the actual values there, I have initial position is 0 meters, right? So that's the top of the roof, we'll take to be the origin. So 0 meters plus 15 meters per second times t plus 1/2 times negative 9.8 meters per second squared times t squared. So that's our position function. Plug in a time, 1 second, 4 seconds, and you get the result. Our velocity function, so remember velocity at time t is equal to whatever your initial velocity was plus g, negative g. Well, I should put negative up here technically too, times the time, right? And so for our expression, for our scenario, we need an initial velocity of 15 meters per second plus negative 9.8 meters per second squared times whatever the time component is. Okay, so we just have to plug in 1 second and 4 seconds and we'll have our result. So if for time t equals 1.0 seconds, what do we have? Well, for position, we can just plug in 1.0 seconds here and we get 15 meters per second times 1 second plus 1/2 negative 9.8 meters per second squared times 1.0 seconds squared, right? And so notice the cancellation here. I get 15 meters here plus, this would be negative 9.8 times 1 divided by 2, which is negative 4.9. And so negative 4.9 meters, right? And so the whole thing is equal to 10.1 meters. And what does that mean? It means above the building. So 10.1 meters above the building. So position at t equals 1.0 seconds is 10.1 meters above the building. Okay. What is the velocity at 1 second? The velocity at 1 second, well, it's going to be equal to 15 meters per second plus negative 9.8 meters per second squared times 1 second. Okay, and when you crunch all of that, you get 5.2 meters per second. Okay, and the ball is traveling upward still, which is reasonable, right? If you throw it at 15 meters per second, it's not going to hit its peak in less than a second, so it's still traveling upward at 5.2 meters per second. But it's obviously losing velocity, right? Velocity is trimming down because gravity has got a hold of this ball and is slowing it down, right? Okay, now what about 4 seconds? What about at 4 seconds? Well, the position at t equals 4 seconds is 15 meters per second or times 4.0 seconds plus 1/2 negative 9.8 meters per second squared times 4 seconds squared. Okay, and so that's going to be what, 60 meters plus, now this would be negative 9.8 times 16 divided by 2, and it'll be in meters, of course, right? Seconds and seconds squared will cancel here, and so in the end you're going to get negative 18.4 meters. Now, what does the negative signify in this instance? That just means that we're below the top of the building. So negative 18.4 meters below the top edge of the building. Okay. Okay, so the ball's gone up, right? You started here, it's gone up, and now it's come back down. So 4 seconds in, it's like somewhere like that. Right, this being your building here. Okay, and so this distance here is negative 18.4 meters, at least in my drawing. Okay, so that's where we're at 4 seconds. Okay, how fast is the ball going at 4 seconds? The velocity at 4 seconds is equal to the initial velocity of 15 meters per second plus the acceleration, negative 9.8 meters per second squared, times the time, which is 4.0 seconds. And what do we get there? When you crunch all of that, you get negative 24.2 meters per second. Right? And the fact that it's negative means that the ball is traveling downward. Right? And so in our idealized scenario here, the ball will continue to gain velocity in the downward direction until it strikes the ground, right? There will be no, there's wind resistance is not a factor here. There's no like terminal velocity concept. The ball is just going to continue to gain speed because acceleration is in the direction of the velocity. It's just going to continue to gain velocity in the downward direction until it hits the ground. Perfect. Okay, perfect. So that's part A. Now what about part B? So what were we asked in part B? Well, in part B, we want to find the velocity when the ball is 5 meters above the building. So find the velocity when the ball is 5 meters above the building. Right? There's different ways to do this. Right? You could use the position formula and determine the time, determine when the ball is 5 meters above the building and figure out what the time is, and then plug that time into the velocity formula we just used to determine the velocity. Another way to do it would be to use a velocity formula directly. So we do have this. We do have this, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times t final, position, y final minus y initial. Okay, so we could use something like this, right? So this is a formula we've seen before. This is one of our kinematics formulas. So this is the change, this is the displacement here. Okay. And so we can plug in our values, our known quantities. So we have v final squared, that's what we're interested in. We want to know that. So we better have all of the other pieces, and we do. So the initial velocity is 15 meters per second. And we square that. Plus 2 times the acceleration, which is negative 9.8 meters per second squared. Times the displacement here, right, times y. Now what is y? So sorry, yf minus y0. So we're interested in knowing the velocity when the ball is 5 meters above the building. So 5 meters would be the final position, and the initial position we take to be 0. So this would be like 5 meters minus 0 meters. Okay, so there you go. So if we use this, we can just dial in directly to the final velocity using the position and the acceleration and the initial velocity. Okay, and so when we do that, we get 15 meters per second squared plus 2 times negative 9.8 meters per second. We want to make sure that we kind of simplify the thing a bit before we start doing the actual calculation. But altogether, this whole side here is equal to 127, and then the units get a little strange here. It's meters squared by seconds squared. Okay, but that's okay because we're looking for velocity. This is the square of velocity, so that makes sense. So the actual velocity would just be the square root of that. So the final velocity would be the square root plus or minus the square root of this. like so. And if you plug that into a calculator, you get plus or minus 11.3 meters per second. Now, how do we make sense of this plus or minus? There's technically two answers, right? The fact that we get two values in this instance actually makes sense, right? Because frequently when you take the square root to solve a quadratic, often you will disregard one of the solutions. But in this case, the ball goes up and then it comes back down, doesn't it? Right, and at some point is 5 meters. Right, and so what this is telling you is that on the way up, we're doing 11.3 meters per second positive. On the way down, we're doing 11.3 meters per second negative. Right? So you have different signs depending on whether you're heading up or whether you're heading down. Okay, so both answers are legitimate since the problem just said 5 meters. Didn't say the first 5 meters or the second 5 meters. Okay, so that's part B. What about part C? What did we have for part C? Part C asked us to find the max height reached by the ball. Okay, so find the max height reached by the ball. Right, now this is a common scenario. This is a common kind of thing to ask. So when the ball is shot up, it's got an initial velocity of 15 meters per second, and as it's moving upward, it's losing velocity, right? Because gravity's got a hold of the ball and is slowing it down. Technically, the acceleration is in the opposite direction of the velocity. So when the ball is at the very top, technically the velocity is equal to 0 at that point. There's a point in time, an instant in time, where the velocity of the ball at the top of its trajectory is actually equal to 0. And so that's the key idea that we want to use to solve this problem, to figure out this height, right? And so we can use, there's a couple of different ways to do it. We can use the same equation that we used in the previous one to determine this problem, though. So we can use v final squared equals v initial squared plus a times y, or sorry, a times g, times plus 2 times a, sorry, and then y minus y naught. Okay, so that's the equation. It's the same equation as what we just used. For some reason, I had a hard time saying the word a there, or 2. Okay, and so the key thing here is that we want to know when the final velocity is equal to 0, right? And so we say 0 meters per second quantity squared equals 15 meters per second quantity squared plus 2 times, now acceleration is gravity in the negative direction, negative 9.8 meters per second squared. And now the position y is actually what we're after here, isn't it? We know y naught is 0 meters and y is the quantity we want to know. So I'm going to write it all out. Y minus 0 meters. Okay. Now this whole thing can be simplified. We've got 0 equals 15 meters per second quantity squared minus 4.9 meters per second squared times y. Okay, so this is really what we are dealing with. And so we want to solve for y, and we can do that by subtracting 15 meters per second squared on both sides, and then dividing by this other term here, this piece here. And so what we get is negative 15 meters per second quantity squared divided by negative 4.9 meters per second squared equals y. Okay. And I think you can see that meters is what you're going to be left with here. You've got meters squared second squared over meters over second squared. So one of the meters will be left. And so you actually end up with y, and you can just do this arithmetic on your own. You get a y equals 11.5 meters. Okay, when you do that division. Okay, right? So that's one way to find it. Another way to find it, we'll go through just a secondary approach, just to kind of emphasize this idea that there are multiple approaches to these problems, right? So while there are 3 kinematics equations, you don't always need, you can go a long ways just using a couple of them, right? Another way to work this Another way to solve this would be to use velocity, the final velocity is equal to the initial velocity plus acceleration times time. And so you start with this, and you say, I know that the final velocity needs to be 0. I know these other pieces, so 0 meters per second equals 15 meters per second plus negative 9.8 times t. And I can use this to figure out t, right? So t is equal to negative 15 meters per second divided by negative 9.8 meters per second squared. And when you do that math, you get 1.53 seconds. Okay, so I figured out how long it takes for the ball to get to its maximum height. It takes 1.53 seconds roughly, right? I can then use this in a standard position function. So we can plug this time into y final equals y initial plus v initial times t plus 1/2 acceleration times t squared. I can plug that time into this expression to figure out the height, the actual position. Okay, and so doing that, I would say y is equal to the initial position is 0 meters plus 15 meters per second times 1.53 seconds, right? Plus 1/2 times negative 9.8 meters per second squared times 1.53 seconds squared. Okay, and that's just a straightforward calculation, and when you do that, you do indeed get 11.5 meters. All right, so the height that the ball reaches, again, is 11.5. All right, so both solutions give you the same answer, as you would expect, right? As you would expect. Okay, and then part D, finally, for this problem. Part D is a question of what is the acceleration of the ball when it is at its maximum height. Okay, so I've got this ball, I throw it up, it hits this high point, and then it comes back down. All right, so what is the acceleration here? Well, this is kind of a trick question, right? The previous part C, we discussed how at this highest point the velocity is equal to 0. But what about the acceleration? What's the acceleration at the top of the ball's trajectory? Well, it isn't 0, right? If the acceleration at the top of the trajectory was 0, the ball would go up and it would just stop there. It would just sit. It would hover in midair at the top of its trajectory. But that's not what happens. It goes up, it pauses for an instant, and then it comes back down, right? And that means that the acceleration is not equal to 0 at that point, right? Otherwise it wouldn't move, it would just stay, right? So the fact that the acceleration is not 0 at the top, and coupled with the fact that gravity doesn't just turn off when the ball hits the top of its trajectory, means that the acceleration is the acceleration due to gravity. So the acceleration at the top of the trajectory is negative g, negative 9.8 meters per second squared. So a little bit of a trick question, just kind of trying to make sure that you understand that the acceleration is not equal to 0 at the top, just the velocity. Okay. Let's actually do a bonus part for this problem, right? So a part E. So for part E, just the same physical scenario. The question we're interested in is, when is the ball When is the ball 5 meters below the top of the building? Right, so I've got my ball here. I've thrown it up. It hits the high point. It starts to come back down. We've said that it'll accelerate indefinitely until it hits the bottom, or until it hits the floor. But at some point, presuming this is a tall building, it's going to reach a position of -5 meters in our coordinatization here. And so that would be the point where the ball is 5 meters below the top of the building. The question is, when does that happen? Given the setup, when does that happen? Okay, and we can, to solve this problem, we can just use a position function, right? So we can use the position function, y equals y naught plus v naught t plus 1/2 at squared. Okay, and for this problem, let's write in with gravity. I'm going to switch pages here. Actually, so we can use y equals y naught plus v naught t plus 1/2 -g t squared. Okay. Now what we're doing is we want to solve this expression for t, right? We're going to plug in a final position, and we know initial position, we know the initial velocity, we know the acceleration due to gravity. So we know everything here except for t. We have to figure out what t is, right? And so what you're going to end up having to do here is solve. You're going to have to solve a quadratic formula for this. You have to solve a quadratic equation for this. This will require solving a quadratic equation. Okay, and you may remember that if I have an expression of the form ax squared plus bx plus c equals 0, then there's a standard, there's a closed form solution for this, right? Basically, we can say that x is equal to -b plus or minus b squared minus 4ac over 2a. So whatever a, b, and c, the terms, the coefficients in these terms happens to be, we can just take those and plug them directly into the quadratic formula, and it spits out two solutions, a -b plus solution and a -b minus solution. Okay, and so the point of this example is to just recognize that we can just know straight ahead that we're going to have to use this formula, and we can just plug this thing directly in. We have to do a little bit of work to it, right? So we first get our formula into standard form, meaning this form up above, ax squared plus bx plus c equals 0. Right, and the way we do that is we basically need the whole thing set equal to 0. So we're going to subtract off this final position term from both sides. So we're going to bring this to the other side, basically. So we can write it like this, -1/2 g t squared plus v naught t, and then plus, and we'll say y naught minus y final. All of that equals 0. Okay. And I'm actually going to switch the signs just to make the arithmetic a little easier. I don't want the negative out front here, so I'm going to write this instead as 1/2 gt squared minus v naught t, and then plus y final minus y naught. Okay, so it's the same thing. I'm just doing a little bit of algebra. And now I can plug these terms directly into the quadratic formula. Okay, so let's write this out. So t is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. And so I can just plug these terms in. This is my a right here. here's my B, and then this is my C, right? So I get negative V naught plus or minus the square root of negative V naught squared minus 4 times 1/2 G times Y final minus Y initial. Okay, so I got the square root there, all divided by 2 times A, and remember A is 1/2 G. Okay, right, so I've got the whole expression here. All I really need to do is just plug in all the quantities, and away we go. Right, so let's simplify this a little bit first. So I've got V naught out front plus or minus the square root of V naught squared minus 4 G over 2. Actually, I'm going to write minus, well, we'll just leave it like this. Minus 4 G over 2, and then YF minus Y naught. And then on the bottom, I'll just write G, right? 1/2. 2 times 1/2 of G is just G. Okay, let's plug all the quantities in. Okay, and so I get 15 meters per second plus or minus the square root of, and now this will be 15 meters per second, quantity squared, and then plus negative 4, sorry, minus 4, and then negative 9.8 over 2. Okay, and then negative 5 is the final position I'm interested in. The initial position, of course, is 0. These are meters. All divided by negative 9.8 meters per second squared. Okay. Alrighty. Okay, and then we can simplify all of this all down, and long story short, we get 2 answers. Well, we get 15 meters per second plus or minus 11.27 meters per second, all divided by negative 9.8 meters per second squared. And so the long and short of it is that I get 2 answers, 3.36 seconds, or in the other case is a negative time, so negative 0.30 seconds. So which one of these is the correct answer? Okay, so let's think about what's happening here, right? I throw the ball up, it comes back down. I'm interested when it crosses this line. So one of these answers is, in particular this one, is telling me the time when the ball is there. What's this other one telling me? Well, the other one is telling me, you know, where the ball would be here, right? So there's 2 problems with this one. First of all, it's not on the trajectory of the ball, right? And second of all, like, it's a negative time. So this is actually referring to the time 0.3 seconds before the ball left your hand, right? So this answer is not relevant. This is the one that we're interested in. This is the one that matches up, aligns with the physical problem. Okay. All right. Very good. So that's the first big problem. So these are good problems. We've got a couple more here. So the second problem that we'll look at is somewhat shorter. The second problem we're going to look at is a problem that has to do with 2 bodies moving in the same system with different acceleration. So I'll just write 2 bodies with different acceleration. This is also a very common kind of scenario that you'll see in a lot of physics courses. I mean, it's a real world kind of example. These things happen all the time. So I'll read the problem out and then we'll write it down. So a car passes a corner with constant velocity of 15 meters per second. Now, just as the car passes the corner, a motorcycle, which was previously at rest, begins to accelerate in the same direction with constant acceleration of 3 meters per second. Okay, so that's the scenario. Let's write it out. So a car passes a corner, or a sign, whatever you want, however you want to think about it, passes a corner with constant velocity of 15 meters per second. So constant velocity means the car is not accelerating at all. It's going a constant speed. So there's no acceleration one way or another. Now, just as the car passes the corner, a motorcycle, which was at rest, a motorcycle which was at rest begins to accelerate in the same direction as the car. Right, begins to accelerate in the same direction with constant acceleration of 3 meters per second squared. Okay, so that's the idea, right? So we've got some kind of a corner here, right? And you've got a car kind of zooming past this corner. Okay, so this will be the car. Okay, and the car has constant velocity, and we'll just denote it as velocity of the car is equal to 15 meters per second. Right, the fact that it has constant velocity means that the acceleration of the car is equal to 0. Okay, 0 meters per second squared. Now, there's a motorcycle kind of parked here, we'll say. Right, and the motorcycle takes off. It's at rest first, and it takes off as soon as the car reaches it. The car is obviously going faster, so it's going to zoom way ahead of the motorcycle, but the motorcycle has acceleration. Okay, so there's the motorcycle. Now, the motorcycle's initial velocity, the initial velocity of the motorcycle is equal to 0. But the motorcycle has acceleration. And the acceleration of the motorcycle is 3 meters per second squared. Okay? So that's the scenario, right? So you've got this motorcycle and this car, and they're kind of tangled up in this scenario. So three questions. Part A, first question, how long until the motorcycle catches up to the car? How long until the motorcycle catches up to the car? Okay, so obviously the motorcycle is going to catch up to the car. It has some acceleration. The car is a constant velocity. And the car might start out going way faster, but since its velocity is constant, the motorcycle is eventually going to overtake it, speed-wise and position-wise. So that's part A. Part B is, what is the motorcycle's speed at the point in which it overtakes the car? What is the motorcycle's speed at the point in which it overtakes the car? Okay. Right, so, obviously that's kind of straightforward. It's going to overtake the car. It's going to have a certain speed. It'll be going faster than the car. How fast will it be going? All right, and then part C is, how much distance beyond the corner has each of the vehicles traveled when the motorcycle reaches the car? How much distance beyond the corner have the vehicles each traveled at the point when the motorcycle reaches the car? Okay. Right, so pretty clear. I think these three problems are pretty straightforward. Again, please pause the video and make sure you give these a try. Try to solve these problems, these three parts on your own before reading or before watching the video and reading its solution. Okay, so let's go ahead and solve them. All right, I've assumed you've done your homework and tried to solve the problems already. All right, so part A, right, we've got the car speeding past the motorcycle initially, but the motorcycle is accelerating and is going to overtake the car's velocity and then eventually overtake the car's position. And so the question is, how long until that happens? How long does it take for this motorcycle to reach the car? Okay, and so the idea here is there's, again, several ways to solve this problem. Probably the most efficient way would be to start with two position functions, right? So you've got the position of the motorcycle, right, which is equal to the motorcycle's initial velocity plus the motorcycle's initial position plus the motorcycle's initial velocity times time plus 1/2 times the acceleration of the motorcycle times t squared. So you've got that one. This is basically the position function for the motorcycle. You've got the same kind of thing for the car, right? So the position of the car is equal to the initial position of the car plus the car's initial velocity times time plus 1/2 of the car's acceleration times time squared. Okay, so you've got these two expressions. Now, we're interested in when will the motorcycle catch up to the car, which is basically a fancy way of saying, another way of saying, when will the car's position and the motorcycle's position be the same? When will they be equal? Okay. And so they'll be equal, wherever they're equal, that'll, basically setting these two position functions equal to one another is how you would model that scenario, right? And so if we set these two position functions equal to one another and solve for t, we will get the answer, basically. Okay. Now, each of these can be simplified a great deal before we actually start doing the algebra, so let's actually plug in the quantities and see what we are dealing with. So you've got the position function for the motorcycle. We'll start with that. It's just like with the car, it's going to start at 0 meters plus its initial velocity, which was 0 meters per second, times the time, plus 1/2, and then its acceleration. The motorcycle has acceleration. It's 3 meters per second squared, times time squared. So that's and this whole thing obviously can be simplified down to just 1/2, well, actually 3/2 meters per second squared times time squared. Okay, so that's the whole expression for the motorcycle's position. Now what about the car? The car again starts at 0 meters. That's where we just start. We start our axis system at the corner, right? So 0 meters plus 15 meters per second, right? It has an initial velocity, right? But the car has no acceleration, so this would be plus 1/2 0 meters per second squared times t squared. So this guy simplifies down to just 15 meters per second times t. Right, so both of them just boil down to just a single term. Okay, and so if I set xm equal to xc, that means I'm saying 3/2 meters, so basically setting these two things equal to one another. Right, just like that. Okay. And you can think about this as, again, this is another quadratic equation, right? And so I could say 3/2 meters per second squared t squared minus 15 meters per second times t equals 0. You could use the quadratic formula to solve this problem. You can also recognize this one can be solved just more simplistically by just factoring out a t, right? Since the c term is equal to 0. So I could say t times 3/2 t minus 15 equals 0, right? This is basically the equation I have to solve. So factor a t out of both terms, basically. Right, and so I've got two options. I can say t is equal to 0. So obviously the positions are the same at t equals 0. Makes sense. They're both at the corner. And or, more interestingly, I can say 3/2 t minus 15 equals 0. Right, and so obviously the second solution is the interesting one. And so what we would say is that 3/2 t equals 15, and so that means t equals 15 divided by 3/2, which is 10 seconds. Okay, so 10 seconds into this scenario, the motorcycle overtakes the car. Right, so the motorcycle's sped up sufficient that it actually overtakes the 15 meters per second and actually overtakes it enough to catch up to it. Okay, and so that's part A. Part B is how fast is the motorcycle going when it reaches the car? So how fast is the motorcycle going when it reaches the car? Right, so we already know it takes 10 seconds, so this is just as simple as plugging in 10 seconds into a velocity formula. So velocity final is equal to the initial velocity plus the acceleration times the time. Right, and so we can easily plug this in. So we've got 0 meters per second is our initial velocity plus 3 meters per second squared acceleration for 10 seconds. Right, means that the motorcycle is going 30 meters per second at the point when it reaches the car. Remember, the car's only going 15 meters per second, so it catches up pretty fast, doesn't it? And then finally, part C of this problem asks, what is the position of the car and the motorcycle when they meet? Right. So how far away from the corner are these two vehicles when they meet one another? Right, and so the position of the car and the motorcycle should be the same when the motorcycle reaches the car, right? Again, so that happens at 10 seconds, right? 10 seconds in. That's kind of the key time, right? That's the time when everything kind of comes together here. So really, we can use the position function for the motorcycle or the car and just plug in 10. So let's use the car. So the position of the car at 10 seconds is equal to 15 meters per second times 10 seconds. And then all of the other terms we saw earlier were 0 plus 1/2 0 acceleration, right? And so this is just equal to 150 meters. Similarly, we could use the position function for the motorcycle, right? And the motorcycle is moving at 0 meters per second initially. Its initial velocity is 0 meters per second for 10 seconds, but it's got this acceleration term, so 1/2 of 3 meters per second squared times 10 seconds squared. Right, and what do we get here? So this is 0, and we get 1/2, and then this is 100 times 3, so basically 300 meters squared. Just meters, which is 100 and so this is 1/2, 150 meters. Same answer. Obviously, you should get the same. Okay, and so that is how far away from the curb we are when the two vehicles pass one another. Okay, perfect. All right, and so just one more problem for this problems and examples lecture, and this one is fairly straightforward, but it's another scenario that we need to have some experience with, and so I'm just going to call this one freely falling coin. Okay, so the idea here is that, and I'll read it and then write it, and then we'll work it out. So a coin is dropped from a tower. The coin starts from rest and falls freely. So I'm holding the coin out, and I just let go. Right? Assume no air resistance, assume idealized conditions. Compute its position and velocity at t equals 1 second and t equals 3 seconds. So a coin is dropped from a tower. Okay, it starts from rest and falls freely. Okay, and so what we're just interested in is compute its position and velocity at t equals 1 second and t equals 3 seconds. So this is a very straightforward problem. Okay, and so simple setup. Let's just draw a simple little picture here. I'm standing here, I have a coin, and I just drop it. And it's going to obviously go down. So g equals negative 9.8 meters per second squared. That's going to be the acceleration acting on the thing. And the initial velocity is 0. There's nothing else happening here, right? So the position function can be, the basic position function can be used. So y final equals y initial plus v initial t plus 1/2 a t squared. Okay, and so for our problem, the initial, we'll say we'll take this to be the y-axis and this to be the x-axis, and we'll set this to be 0, 0. Right, and so we'll say the initial position is 0 on the y-axis. Okay, and so we've got 0 meters plus the velocity, which is 0 meters per second, times t plus 1/2, and then the acceleration is negative 9.8 meters per second squared. Okay, and so this can all be simplified down to just negative 4.9 meters per second squared times the time squared. That'll tell us our position, and we can use that for time equals 1 and time equals 3. And then our velocity, we can use this guy, so v final equals v initial plus acceleration times time. And so here we'll say v final will be equal to our initial velocity, which is 0 meters per second, plus our acceleration, negative 9.8 meters per second squared, times time. And so this is really just negative 9.8 meters per second squared times time. Okay, and so then we can just plug in the times we want, and we're set. So when t equals 1 second, you just need to solve y of 1 second, and that's just this guy, right? So it's negative 4.9 meters per second squared times 1 second squared, which is negative 4.9 meters. And the velocity at 1 second is just negative 9.8 meters per second squared times 1 second, which is negative 9.8 meters per second. Okay, so that's the position and velocity of the coin after 1 second. And then when t is equal to 3 seconds, it's the same exercise, isn't it? So y of 3 seconds is equal to negative 44.1 meters, and and velocity at 3 seconds is equal to negative 29.4 meters per second. Okay, so there you go, real simple. Now, a question that I would have for you is, so if we were given the height of the tower, we could ask how long until the coin hits the ground. We could also ask how far from the top of the tower is the coin when it reaches, minus 100 meters per second. Right? We could ask these kinds of questions, right? All kinds of position and velocity types of questions, right? But yeah, so this just kind of gives you a setup. So this one is interesting because it's just something falling straight down. There's no initial velocity. There's no intersection of things. It's just the force of gravity accelerating something. Okay. All right. So that's where we'll end this lecture 6, problems and examples from section 1, motion along a straight line. Now in our next section, we're going to switch to motion in 2 and 3 dimensions. And we'll start with, again, looking at position, velocity, and acceleration. And basically the same concepts we've covered up to this point, we're just going to expand into multiple dimensions, which means we're going to have to introduce the idea of position, velocity, and acceleration vectors. But that's next time. We'll end this one here. Take care, everybody.